Hi, my name's Peter Landon. I am a product manager with NSP, and today I'd like to spend a few minutes with you to talk about the benefits of NSP IP optical automation and how it can help simplify your day-to-day tasks and save you money. So I'm going to start with a brief introduction on why IP optical integration is important and how NSP can facilitate a different way of working utilizing automation and tool integration. I'll go through a handful of use cases and explain how the different features of the cross-domain coordinator application fit within the suite of apps in the NSP. I'll also touch on what we're thinking about for 2022 and beyond, which I think you'll find interesting. Finally, I'll touch on some work we've done in the past year with multi-vendor demos. So why use IP optical automation? The evolution and integration of IP and optical transport infrastructure is a critical success factor because this is an area that continues to be dominated by operational silos. And these silos hold back innovations and improvements that can be brought to bear on both the planning and the operating functions. Operators will often rely on multiple teams and experts assigned to specialist functions within a layer. Particularly in large, well-staffed network operations groups, the person who starts investigating IP failures is often not the one who does troubleshooting in the optical domain. And in smaller installations, a single person may attempt to troubleshoot the entire network using different disparate tools. In either case, better coordination and tools can improve operational efficiency and network availability. This gap has been further exacerbated with the introduction of 400ZR, which we're going to get into later in the discussion. Over the years, there's been an ongoing effort to address these coordination issues. And even though SDN is an overused term, we believe that SDN-based solutions enabled by open interfaces such as TAPI have matured to the point where IP optical integration is achievable in multi-vendor environments. This new multi-layer coordination capability allows the introduction of a new mode of operation that unlocks various cost synergies, such as multi-layer protection and restoration, and improved visibility and control of the IP optical network, even in multi-vendor environments. These benefits contribute to service quality, velocity, and efficiency, really all of the advantages that are very difficult to realize with disjoint IP optical domains. Before we start looking at the use cases, I'd like to mention that these are really just a few examples, and once you have the full accurate multi-layer topology, there are many workflows that can be automated. CDC is only part of the NSP suite of applications, and combined with the workflow manager and the intent manager, the number of outcomes is really limitless. So let's take a look at the main set. With cross-domain coordination, we focus on business outcomes, which are implemented through use cases. The outcomes fall into three categories: discovery, correlation, and optimization. The discovery use case provide insight and visibility into cross-domain topologies of networks. These use cases are non-intrusive and informational, and they're all about visualizing an accurate depiction of your network. So topology discovery and diversity analysis fall into this category. Correlation includes the coordinated assurance and coordinated maintenance use cases, and these allow events and activities across layers to be synchronized and associated to make operations more efficient. Then finally, optimization includes optical service provisioning and enhanced resilience. These use cases allow the user to make changes to the network in an efficient and automated fashion, which can result in significant OpEx and CapEx savings. Now, the first use case I'd like to talk about is topology discovery. This one is important because it forms the basis of all the other use cases. Traditionally, operators have had to manually into the details of topology, and particularly the connection points between the IP and the optical network layers, into spreadsheets or similar informational repositories. Obviously, this manual effort is time-consuming and error-prone. A better way to tackle this is to use an embedded protocol to detect and record the topology and connectivity. The cross-domain coordinator application takes advantage of this functionality. This accurate discovery of the actual deployed topology allows good operational decisions to be made, which lead to reduced probability of service outages, simpler troubleshooting, and it can also be very helpful for network planning. The next use case in the discovery category is path diversity. Path diversity is needed for IP links or for IP services, but paths may not be fully diverse in the optical domain. Without knowledge of the underlying network, a failure could impact both primary and secondary paths. The cross-domain coordinator can perform real-time diversity analysis for IP services traversing the optical network. This non-intrusive analysis checks the end-to-end path diversity for 2 or more IP services transported over an optical domain. At the completion of the analysis, a detailed report is generated, and the report contains a summary of the run, lists all of the groups which are successful, the groups which failed, and any groups that would be part of your own exception list. This is a good proactive way to reduce the possibility of service outage. Next, we have the correlation use cases, which are primarily focused on correlating events between the IP and the optical domains. The first one is coordinated assurance, which bridges the gap between alarms that occur in the IP domain that actually have a root cause in the optical domain. Often, problem symptoms can mask root causes, and root cause faults can cause floods of related secondary alarms. As operation folks know, when you're faced with a flood of alarms, it can be overwhelming to determine the root cause of an issue. And the last thing you want to do is jump between different tools that have no connection. Then you may be faced with inter-team communication issues due to the siloed nature of the teams that occur in many companies. NSP addresses these issues with alarm correlation. The fault management application, together with CDC, can provide deep insight into the root causes of alarms, allowing the operator to quickly navigate through the noise. Now let's turn our attention to the optimization use cases. The applications I've described so far have all been passive and didn't impose any changes to the network. On the other hand, coordinated control allows you to actively manage the network to provide, for example, coordinated maintenance. A common issue that operators deal with is avoiding traffic disruptions during scheduled maintenance activities. The capabilities of the cross-domain coordinator are well suited to prevent impact to the IP services during this planned maintenance. The application has the ability to coordinate and orchestrate traffic at the IP and the optical layers through one interface and on a single pane of glass. This, of course, is particularly relevant for unprotected optical services. The way it works is you simply click on an optical link in the network, and you can simulate the impact of putting that link into maintenance. If you're satisfied with the results of the simulation, you can go ahead and put the link into maintenance state. The LSPs are then proactively rerouted to keep IP traffic away from the affected optical links during the maintenance activities, as well as during the restoration of the link. And the NSP ensures that performance targets and policies are still maintained through the maintenance activity. Another optimization use case is focused on saving CapEx by reducing router and optical ports without sacrificing resiliency. This can be an effective strategy for operating a hotter network by reducing equipment redundancy without, of course, reducing availability. The last use case I'll touch on is the cross-domain connection management, which is a creation of LOIs or layer 2 connections across different optical domains. Traditionally, to create a service across multiple third-party domains, complex manual provisioning is required. However, the cross-domain coordinator app provides an operator with a simplified provisioning capability to create LOIs or optical services in a complex deployment, even where connectivity crosses multiple optical domains. In addition to specifying endpoints, the operator can also define constraints on the link, such as strictly co-routed or strictly diverse, or they can include or exclude nodes in the path. The key to this capability is utilizing industry standard interfaces such as the ONF TAPI, which allows the cross-domain coordinator apps to communicate with third-party controllers to provision these services. This service connection capability allows faster time to revenue for new services, which results in OpEx savings and, again, a more satisfied customer. So I'd like to turn now to 2 new use cases that were introduced this year and will be the focus of deployments in 2021 and 2022. The first one is elastic IP optical bandwidth, and I'm really excited about this use case, which was introduced in release 21.6 of NSP. Using this capability of the cross-domain coordinator, you can introduce the ability to expand and contract lag bandwidth dynamically. The capability is best described with an example. Imagine a network that has changing bandwidth demands depending on the time of day. In the morning and throughout the business day, you've got a very high north-south traffic demand, perhaps due to users accessing data on the servers. In the evening, that traffic wanes and it's replaced by heavy east-west traffic due to backups or migrations. Without dynamic control, you need to size the network for the worst case in both directions. With elastic IP optical bandwidth, you have the ability to program a time of day where your north-south lag will contract in size, freeing up router ports and optical ports. Once these ports have been freed up, the cross-domain coordinator will expand your east-west lag capability automatically, utilizing the new freed up ports. The cross-domain coordinator can handle all of these port assignments and configurations automatically and reliably. Now keep in mind that the number of IGP links are not affected and you're not changing any policies. You're simply increasing the bandwidth of that particular lag. And we could even take this a step farther. When you combine a new elastic lag function with the extensive analytics capabilities of the NSP, you can really begin to harness the power of automation. Using the Insight Administrator, the user can create an indicator which will monitor bandwidth on selected ports. If the traffic exceeds a specific threshold, a Kafka event will be triggered, initiating the lag expansion automatically. These are just a few examples of what can be accomplished with this new powerful capability. Now I'd like to take a few minutes to talk about 400ZR and how our management solution is a little different than others out there. I like to describe the management requirements as a gradient, depending on the span and the type of transceiver that you're using. This can range from the simplest gray optic or unamplified 400ZR link through DWDM point-to-point connections, all the way to a fully featured mix of transponders and ZR plugs. Let's start with the gray optic for short reaches, for example, to a transponder. There's not much to it. It's on or off. There are no power levels. You've either got a link or you don't. This is built into your current management system, and everyone has that. And even as you move into plugs with variable power, like a ZR and an unamplified application, this is still pretty simple. And you might even use a CLI, depending on the number of links. But when you start to get into DWDM applications, even with a simple FOTM, you're going to need maybe a channel plan. You still need an easy way to validate that the link is operational, ideally through a dashboard. And finally, depending on the channel count and placement of the channels, you might need a power ramp function to avoid affecting existing channels when new ones are added. This is where having automation capabilities can be very useful, providing a foolproof, consistent method for managing the lifecycle of your ZR links. So as we go beyond the single span, let's look at multiple spans. Here, in addition to the automation we just discussed, you're going to require optical channel monitoring and active power management to avoid crosstalk penalties. Contributions at the OIF have shown that you want to keep adjacent channels to within 1 dB of each other. Using the NSP, you can reliably handle large channel count deployments. And as we move to even longer reaches that include Raman pumps, the need for dynamic gain equalization, or DGE, is required, adding further complexity to the management story. Finally, when ZR links are deployed as part of a lowest TCO architecture that includes DCOs, transponders, and ROADMs, perhaps as a part of a brownfield network, you want to have the native optical controller handle the complex functions such as power management, PCE. This is another area where NSP is uniquely positioned and differentiated from other vendors. NSP is an integrated solution that simplifies the workflows associated with provisioning services, seamlessly building on the specialized capabilities of the optical controller when it's needed. All of this is done, again, through the standard interface such as TAPI. So if there's one thing I'd like you to take away from this presentation today, it's that managing 400ZR connections in any configuration or any architecture is simple and it's flexible when using the NSP. We approach the lifecycle management of the ZR link in the same way as we approach all services in the NSP, and that's through intents. And if you're not familiar with intents, in its simplest form, it's all about describing what you want out of the network rather than how it gets implemented. Whether you're dealing with a lower reach point-to-point or a linear connection that requires DGE, the NSP can manage these with a common workflow and a single pane of glass in a model-driven fashion. And when an optical controller is in the mix for hybrid deployments, including transponders, the NSP integrates that end-to-end link management, avoiding alien wavelengths. So I want to briefly introduce a new optical line product that's coming this year called the PSI-CL, which is a compact line system that's model-driven and optimized for 400ZR links. The NSP can manage this line system in a model-driven approach for all elements of the link, avoiding alien wavelengths. This simplifies control and management and unlocks all of the NSP capabilities, including fault management and network supervision. So how is 400ZR going to work with open line systems? In an open line system environment, NSP uses the OpenTAPI interface to discover new ZR topologies and services and allow for new service creation using intents. Assurance is accomplished through network supervision, and in a single pane of glass, you have access to ZR connections in the context of a multi-layer view with easily displayed optical parameters such as channel, power level, and prefix bit error ratios. So what you see here are a few planned screenshots that give you a flavor of what will be available with the 400ZR feature set. You can see on the top shot the integration of the ZR link, which traverses an optical domain. And in the second screenshot, you can see a depiction of the ZR parameters as they would appear on an NSP dashboard. Again, the network visualization is intended to be clear, easy to use, and intuitive. Now, I touched on it a little earlier in the presentation, but what you see here is a screenshot of the intent manager showing a few sample pre-configured intents. For example, you can see an intent called test ZR at the bottom, indicating that there's an intent that is ready to be used to establish a new ZR link. From this screen, you can also edit the existing intents or create new ones. Diving a little deeper into the intent manager, these screenshots are showing you how the intent is edited to create default values for the ZR parameters. You'll notice that the intent itself is based on a Yang model of the link, and that the editing form is actually auto-generated from that model. Once the intent has been modified, the network is synchronized, ensuring that you have a single source of truth related to that ZR link configuration in the NSP database. Last screenshot here, just to show you that in addition to the rich network map visualizations available in the Network Supervision app, you also have a full inventory available in the equipment tree. Here you'll find all the information you need on the plugs, including manufacturer details, part numbers, serial numbers, and all equipment details. Lastly, I'd like to quickly touch on the work that has been done in the past year regarding interoperability with third-party optical controllers. Late last year, we participated in the OIF's multi-vendor transport SDN interop event that occurred in Telefonica labs in Spain. As part of that interop, we were in the lab with Ciena, ADVA, and Infinera, and demonstrated interoperability around the TAPI interface. As mentioned earlier, Nokia is a leading contributor to the ONF TAPI standard, and we're committed to broadening the functional content and the real-life deployments using that standard. Well, I hope that's all. I hope you found this to be useful, and please don't hesitate to reach out if you have any questions. Thanks.